My name is Yuqiao Liang. I'm a postdoc at Woods Hole Oceanographic Institution at the USA, and I'm a relatively new YES member for this working group. Today, we are very happy to have Dr. Min-Hui Lo from National Taiwan University, who studied global sea level rise from a hydrological perspective. And Min-Hui obtained his PhD at California of UC Irvine at 2010, and he's now an associate professor at the Department of Atmospheric Sciences at the National Taiwan University. So before I give time to Min-Hui to present, I want to quickly go through the code of conduct. So first is be polite and be respectful to the speaker and all participants. And also please keep muted and close your video during the presentation. And you can type your questions in the chat box at any time during the presentation or during the Q&A. And I will read your questions out during Q&A. And if time is allowed, I will give you some time to ask in-person questions. So you can use the raise hand buttons. And finally, we record all the contents of the presentation and also Q&A and all the message in the chat box. Just be sure, okay? So if you have any questions, you can raise your hand or put your questions in the chat box. Okay, so now I'll give time to Min-Hui. Okay, please.
Well, okay. Thanks, Yuqiao's introduction, and also thanks for the invitation for the opportunity to give in this webinar. So good morning and good afternoon and good evening, everyone. So today I want to talk about basically it's kind of global water cycle issues. And then I set up the title from the global mean sea level changes to actually is my major focus, the land atmosphere interactions. So as Yuqiao mentioned, right now I'm associate professor at the National Taiwan University in Taiwan. And most of the results I show today actually a lot of helps from Wenying Wu and also Longyou Jian, Ren Jie Wu, Hao Wei Wei, and Li Wei Zhao, and Yanling Guo. Most of them are my previous students. And also a lot of work actually is a collaborations with J.T. Rieger and Ray Anderson, Jeff Emiliadi, my former advisor, and Dongyong Ro and Mel Rodell, Sean Swenson, and Q Hong Tan. Okay, so as we NASA's TOPAX JSON's lost remote sensing satellites tells us that the global mean sea level has risen in the past 20 years from those observations, and the rate is about 3.3 millimeters per year, and this including from thermal expansions and polar ice meltings from, of course, from Antarctic or from Greenland, and also from mountain glaciers. And the other one is the human activities. So usually the human activities can separate into two major parts. One is from the groundwater pumping, which is a positive contribution to the sea level rise. The other one is those dam reservoirs along the rivers, which is another negative feedbacks or effects to the sea level rise. But in total, combine these two human impacts, actually overall the human impacts has a positive contribution to sea level rise. In general, these four different components contribute to the mean global sea level is about 3.3 millimeters per year. However, in 2014, actually there was a very interesting paper from Kazanov's group that basically showing that the mean sea level rise, actually the rate slowed down to a rate of 2.4 millimeters. This is the rate sea level rise changes along the time from the satellite era from 1994 to present. So as you can see that in the beginning it's about like 3.5 millimeters, but after 2002, actually it started declining to like 2.4 millimeters. So the thing is that, okay, what happens? At that time, actually, it's like a global warming hiatus. So basically, at that time, the atmosphere temperature doesn't increase. It kind of reach like steady state. But a period of increased mass loss still being observed from glaciers and ice sheets. So the question will become, where's the water? Why the sea level rise slow down to 2.4 millimeter per year only? So people has suggested that the increases probably in the land water storage has been suggested to have contributed to this slowdown. However, this only is kind of hypothesis at that time. People use a global hydrological model to test it, but no verify with observations. So in 2016, that working with JT Rieger, we try to use a remote sensing data set, which is so-called GRACE. And then these two satellites actually is like one mission, but two identical satellites. So it can actually measure the gravity changes on the Earth, both for the land and the ocean. And from this GRACE satellite, we can actually try to trace the water variations at the month-to-month time scale changes. So the basic idea of the GRACE is, for example, if you look at your left-hand side, these two identical satellites is a GRACE mission. So if the first one passed through the mountains, but because it's attracted by the mountain and also those snow or ice on top of the mountains with the higher mass and the higher gravity. So actually the satellite distance, the first satellite will sense the gravity first or higher. So the distance between these two satellites will be longer. However, when the second satellite also passes through the mountains, it can also sense the mass or the gravity here. So the distance becomes smaller. And then further, after they passing through this mountain and on top of the mountains, the first one is already far away from these regions, but the second one still sense the gravity is here. Again, the distance will become longer again. So basically, what the scientists try to trace the distance changes, then they can refer how much the mass is on the mountains. So if we see the second, your right-hand side figures, after a couple months, maybe the snow is melt, then you can see the distance doesn't vary that much. So we can use the distance changes, try to infer how much snow actually was there in the past couple of months. So this is what we try to call, is the so-called total water storage variations, because it doesn't only measure the snow, it also sense the surface water, soil water, and groundwater. And so we try to use this one, and then to give us many like river water storage changes globally. This is the example. So we can see like GRACE is like a giant scale in the sky that tells you how much weight you have gained, the Earth has gained or lost each month. So this is a simple GRACE time series. So for example, taking Mississippi as an example, you can see not only the seasonality is very clear, you can also see sometimes there are interannual variations. Taking Amazon as an example, that we can see a continuous increasing of the water storage. On the other hand, in Ganges, that you can see a continuous decline of the water storage. So right now, using the GRACE data, actually we can try to track the whole ocean and ice changes using a single observing system. So later I will call it 3 terms. It's called delta S over the ocean, delta S over the land, and also delta S over ice. And ice basically is for the Greenland and Antarctic ice. And you can see that in your right-hand side figures, there are 4 time series from 2002 to 2014 from the GRACE data. So if you pay attention on the blue lines, here basically showing the ocean mass has continuous increasing in the past 10 or 12 years. On the other hand, you can see a 2 continuous decline trend time series from the Greenland and Antarctic. So basically try to show that overall the mass in the Greenland and on Greenland and Antarctic are continuing declining, and most of the water actually flow to the ocean, which we already know. But this is the first time that we can measure how much in terms of weight that ice over the Greenland and Antarctic are melting. And there's another green line here shows the land water storage variations. The tendency is not so clear, but it still shows a little bit of decline. So if we do a very simple linear regression, y equals ax plus b, that if we plot their trend for these 4 different time series, we can use, we can see in your left figure, this bar chart is a partitioning of the ocean mass. So the 1.58 millimeter per year is the ocean mass gained in the past 12 years from the GRACE data. And then on the other hand, the Greenland contribute about 0.77, and Antarctic contributes about 0.49. And this is another term called net land water storage. It's in average, is about 0.32 millimeter per year of the contributions. So overall, these 3 different components, Greenland, Antarctic, and the land water storage contribute to the ocean mass changes about 1.5 millimeter per year in the past 12 years from the GRACE era. However, from the IP5 report, it kind of old right now, but when the paper is published, was published 5 years ago, that is still quite new. So at that paper, we used the IPCCR5 reports data. In that, the most advanced reports tells us that the land glaciers actually contributes to about 0.6 millimeter per year of the sea level rise. On the other hand, the human-driven land water storage, the human-driven, as I mentioned in the beginning, that including the groundwater pumping and also the dam or reservoirs contributions is about 0.38 millimeter per year. So right now there's a mismatch here that because from the GRACE data we know it's about 0.3 millimeter per year of water contributes to the sea level rise. However, from the IPCCR5 reports, it's about 1 millimeter per year of the contributions to the sea level rise. So what happens, there seems one component, one missing component that is not included in the previously AR5 report, which in this paper we define as a climate-driven land water storage. So it's just a simple like summations that there should be another term called climate-driven land water storage about negative 0.7 millimeter per year of the contributions to the sea level rise. So this is kind of the reason why the sea level has been slowed down in the past 10 years because the land contribute less water to the sea, to the ocean, so decrease the sea level rise. So in the paper, we try to mention that the changes in the global water cycle actually causes the land in the past 10 years to act like a sponge. It absorbs more water than previously. It's about 20%. So leading to this sea level rise slowdown. So if we look at this simple diagram about the overall global water cycle, so the unit is the 1,000 cubic kilometer per year. So overall in the oceans, there is, of course, more evaporation compared to the overall precipitation on the ocean. So it's about 40 units more. And these 40 units water has been transported to the land, leading to more precipitation over the land, and most of the water, all of the water should be flow back to the oceans. However, in the past 10 years, it's kind of imbalance between the land and ocean, and this imbalance can actually attribute it to the global warming hiatus issues, because under global warming hiatus is actually like a La Nina-like SST pattern. So the water cell actually has been enhanced. So more water, more precipitation actually happens over the land. So leading to some of the water has been stored over the land, which has not been flowed through back from the river to the ocean yet. So this is one of the reasons the sea level rise has been slowed down. So this is kind of what I just mentioned, that global warming signal on the sea level rise actually is modulated by these natural climate variabilities. So which is like the global warming hiatus in the past 10, well, actually the global warming hiatus is from like 2002 to 2012. Okay, so from the GRACE map, actually we can know more. As I just mentioned that overall the land actually absorbed more water compared to the previous. And this map is a quite famous trend map, which means that if you see some regions with red spots, indicate continued loss. So you can see quite clearly in Greenland or Antarctic or like Patagonia ice sheet or in the Middle East. So a lot of the place the water is lost is actually due to the groundwater pumping or ice melting or less precipitations. However, I would like to draw your attention on these three spots that in the past 10 years, a lot of water actually accumulate over there, which caused the sea level rise slow down. Because previously the number I show you is the global land average. But right now we can know where the water actually stored over the land. And these three spots, particularly for the Australia here, is actually is quite similar to the above figures. These figures is about those inland river basins, or some people call it endorheic river basins. If more water, actually more precipitation over those regions, there is no direct outlet to the oceans. So the water can be easily to accumulate over there. And then they will not just sit there, probably they will infiltrate to the soil and the deeper soil layer or even the groundwater. And they may evaporate to the atmosphere at a longer time scale instead of flow back through the rivers to the ocean within relatively shorter time scale. So this is the particular reasons that usually during a La Nina-like year or La Nina-like climates, more water, more precipitation actually will fall into the Australia and also the South Africa, which is also another inland river basins that make the water easily to be accumulated over in that regions. And this is a passive part, passive trend part. And I also want to draw your attention to another regions which of these red spots. In the past, several studies actually point out from the California to the Middle East and also to the Northwest India and also Northern China plain. These red spots indicating the negative grade trend map, and it's water loss. Most of them are due to the groundwater pumping. And the reason for groundwater pumping is if we overlap the irrigation intensity map. This is FAO's irrigation intensity map. You can see quite clearly that in California, in Middle East, and also in Northwest India, and also Northern China plain is highly irrigated regions. all that, but also these regions are like in a relatively arid regions. So most of the water has to come from the groundwater pumping. So that's why it's a massive groundwater pumping leading to the overall total water storage declining. And actually it can be seen by the GRACE data. And let's take a look at California as an example. The water budget in this heavily irrigated system is very, you can say strange or very interesting, that the observed precipitation is about 370 millimeter per year. On the other hand, the observed evaporation is about 600. So from the water budget perspective, it doesn't make sense, but it's actually a lot of human activities involved here, from the surface water deliveries and also from the groundwater withdrawal, that leading to this very high evaporation rate under these rather arid regions. So the next step we want to show is can the current climate models simulate these reasonable evaporations? Because let's go back to this schematic plot again. The overall, the real or the observed the precipitation is about only 300, but there's almost double of the evaporations. And if our climate model cannot reasonably simulate this, how can we use that for the future projections? So the climate model here, this is just a schematic showing why the climate models. And then particularly I want to show whether the land surface model can simulate these fluxes, because it's over land. The land evaporations is actually processes in a land surface model. So here, I use 9 different land surface model simulations and give those give those models with observed precipitations. So this is observed precipitations Interannual variabilities. This is the model simulated evapotranspiration. So by comparing the precipitation to the evaporation, probably you can think it simulates probably okay, because during the 2006, 2007, there's another drought event in California, which is simulated by the lenses models with less evapotranspiration. However, when we compare to those satellite-based or estimated of the evaporation, you can see that there are a lot of differences between the observed and the simulated. Particularly the peak of the estimated or the observed is around like June, July, August, which is the Northern Hemisphere summer. But the simulated is only during the spring. Actually, it reached the peak at around like March. And the second issue is that the mean is around like almost only like half of the observations. So basically, it indicates that our current lenses models has some biases, particularly underestimate the evapotranspirations when compared to these observational estimates of the ET. And as we know, this is kind of the lenses model physical processes. In the past 20 or 30 years of develop, the lenses models can actually have a lot of processes, physical process. For example, like precipitation, and you have the interceptions, and you have a vegetation which gives the transpirations, and also infiltration into the soil layers and soil redistribution of the fluxes. However, because of lacking, I think, 2 basic human activities, that which is like from the surface water deliveries and also the groundwater withdrawals for the irrigation processes. So because of missing these 2 different processes or components, that makes the the lenses model over those highly irrigated regions underestimate the land evaporation. So we basically try to do what farmers do, but in the models. So we just add the water back to the models and then reconduct the previous simulations. This is something we obtained, that the black line is the model with those two irrigation fluxes. Right now, we kind of, whoa, that's quite a lot of improvement. That to the first order, I think we think that overall the amount of ET or evapotranspirations is simulated reasonably compared to the observed. And also the peak right now is shift to more like during the summertime. Although there are still some drawbacks, for example, in 2004, 2005, like it's kind of underestimate of the simulated ET when compared to the observations. That's because in this simulation, we actually use the same amount of irrigation fluxes all the time from 2004 to 2010 without the Interannual variations. So this should be the reasons that there are still some drawbacks. But to the first order, we think that the improvement should be good enough like to represent the reasonable evapotranspirations over these highly irrigated regions. So a quick recap here that the current models, particularly I'm talking about the lenses models, have quite sophisticated physical parameterizations already. However, lack of these anthropogenic processes usually lead to the underestimate of evapotranspiration. So this is one of the examples we try to demonstrate in this paper. And the next step, we probably want to think about what are the potential impacts of this underestimated ET, because we are talking about the lenses process. And we know if you don't include in the irrigation process, you will get the underestimated evaporation. So how it might affect to the atmosphere? So we actually try to use climate model simulations and using an community atmosphere model. So we simply conduct two experiments. One is a control run, the other one is an irrigation run, because we know that under the control run, the ET actually should be underestimated compared to the observations. So we observe the irrigation water in the model to see how the irrigation run can be different from the control run in terms of the atmospheric responses. And the both simulations are conducted for 90 years, and we focus on the west of the US because we conduct the irrigation experiment only within the Central Valley, California. And then we only focus on the summer only because at that time is the highly irrigated time period. And this is a result showing the local responses of the surface temperature in your left-hand side and also the increased latent heat or evaporations in your right-hand side. The contour shows here is the climatologies. And then the red shaded colors here indicating the decrease of the surface temperature. On the other hand, with increase of the latent heat fluxes over the Central Valley, California regions, which makes quite sense because right now we add irrigation water in the model, in the lenses model. When coupled to the atmosphere, the result still can show the more latent heat fluxes with the decreasing of the surface temperature. However, because the reason why to conduct the climate models is we want to know how the atmosphere, particularly the precipitation responses. So this is the precipitation results we show here. That you basically can see the California in these regions, you don't see much precipitation changes. However, on the coast or Pacific regions, you show decline of the significant decline of the precipitation. On the other hand, in United States Southwest, you can see the increase of the precipitation. So we call here is like asymmetric responses in rainfall after irrigations in the model. And the simple explanation for this one is that because this is in the West Coast regions, is actually in the stratocumulus cover regions. Usually those stratocumulus doesn't rain that much, but it has some drizzles. And right now you can see the changes of the rainfall is quite low. It's only like 0.9 to 1.2 millimeter per month of the changes. But it still shows significant because the changes are, because usually they don't precede. And the reason is because the surface temperature decreases as we show here. So the land sea contrast becomes smaller, leading to the smaller land sea breeze. So because of a smaller land sea breeze, the subsidence over the coastal regions becomes smaller. So the stratocumulus can sustain over there. For usually the stratocumulus is about the life cycle is very long, about 2 weeks, and because it has like subsidence impacts from both the hardy circulation, also from the local circulations. And here in these simulations, we found that the local land sea circulations become weaker. So actually reduce the local subsidences over the coastal regions. So leading to a less precipitations as we see from the previous figures. On the other hand, in the southwest of the US regions, you see the blue spots over here is the increase of precipitation. And we use this schematic plot try to show why there are more precipitations after the California irrigations. So basically in the paper, we found this, some of the water vapor after evaporations from the local Central Valley has been transported from the southwest here to the Arizona. And then because these regions actually is Northern America monsoon regions, and also is land atmosphere interaction is quite strong. So more water vapor transported to here actually kind of provide some fuels or water vapors to these regions, make the precipitations more intense. This is the result we found here. And also it induce more land atmosphere interactions, and then also induce more lateral water vapor convergence from the east and also from the south. Although there are some more water vapor transport out to the north, but overall, there are still more water vapors being accumulated in the southwest regions, leading to more precipitations. The average is about, as you can see, 15%, and also more ETs because it evoke a higher land atmosphere coupling in these regions, so leading to more precipitations. So a simple explanation I try to provide here, why after the California irrigations, actually you can see a reduced precipitation in the coastal regions. On the other hand, increased precipitation in the southwest United States. So it's two different mechanisms that leading to these asymmetric responses in rainfall. Okay, so the left-hand side actually is the semi-5 model average of the latent heat fluxes over the California Central Valley regions. So you can see its peak is around April, May, which is quite similar to the control run without irrigation processes. After the irrigated process is in this blue line. So we actually can try to make two hypotheses that the simulated coastal stratocumulus might overestimate because with a higher land temperature, summer temperature over the California regions. On the other hand, the simulated US Southwest rainfall might underestimate because it missed the extra ET actually from the irrigation process. So this is kind of applications on the current climate model, because if they don't consider those irrigation in these highly irrigated regions, this underestimate of ET might lead to some model simulation biases. And this California study just one example for this. And we also look at the impacts on larger scale monsoon system. Why? Because as we show here, this is a FAO irrigation map. So you can see that in India, there's another hotspot of the irrigation. And the impact of the monsoon system actually is from the reduced surface temperature from the irrigation cooling effects. So during the summer, actually the irrigation can reduce the land-sea contrast. Previously, those studies already shows in the monsoon will become weaker if you consider the irrigation process in the model. On the other hand, during the winter, our previous studies actually shows it may enhance the land-sea heat contrast, because India, after irrigate, it will become cooler, and then the land-sea contrast actually becomes stronger. So in Wei et al., these studies actually found the enhanced land-sea heat contrast and also provide the higher, the winter monsoon becomes stronger. So it's in 2 different seasons, actually you can see the 2 different responses from the irrigation forcing in the Indian continent. So I guess I may run out of time. So I think I will stop here for now. If you have any questions, you can, I think, raise your hand or post on the chat box, and you Chao since will let me know. So I will stop here for now.
Okay, thanks Min-Hui for these interesting topics. So do you have any, if anyone have any questions, you can use the chat box. And now I don't see too many questions on the chat box. So if you want to raise your hand, I mean, I can also allow you to talk in person. Okay, I saw there's one. So I'll let you talk, Climate. Okay. Hey, you can speak.
Hello, good afternoon. Hello, can you hear me?
Yes, we can.
All right. I have a question. Can I go ahead?
Please.
Yeah, please.
All right. The presenter made mention of a model underestimate some parameters of variables, and want to know what actually responsible for that. Is it the matter of parameterization, or what factors that are actually responsible for that in models?
Okay, so when you say the responsible, you mean the underestimated or the overestimated?
Yeah, for model to underestimate some of these variables or parameters that you showed the other time.
So for example, in this, you can see the bottom figures.
Yeah.
So this underestimation of the models from the black lines here. Yeah. So that's the, I would say it's a default model setup with quite good or very sophisticated consider this physical process during the model develop processes. We consider it's the natural variations, but we don't consider the human behavior in the beginning. So the human behavior that in this presentation I want to illustrate is the irrigation processes. That is not included in the model in the beginning. So that's why leading to this underestimation. So if we think about from the physical process perspective, yes, it misses some parameterizations.
Okay.
But of course, we can use a kind of model tuning process to tune a lot of parameters to make the evaporation as like observed in these highly irrigated regions. But still, because the parameter has been tuned, so it may not feasible to distribute it to other regions. So to my opinion, I would say to aid some physical processes is a better way to make the model better. Do I answer your question?
Okay, thank you.
Okay, thank you. I got the other one. I got the other one in the chat box from Marisol Osman. Hope I speak your name correctly. So, do you know if there are any CMIP-6 models simulating irrigation at this moment? And from your experience, do you find computationally expensive to include in irrigation in climate models?
Okay, so for CMIP-6, there are actually more and more models try to include these irrigation processes, and also even from the groundwater withdrawal. And of course, the NCAR model has already implemented the irrigation processes. So that is included in the CMIP-6 simulations. So, and on the other, but there should be more models, but I'm not sure whether they have this kind of archive yet. But on the other hand, the irrigation process actually, it won't require much computational time, because it's just like a process. When we try to understand how to irrigate it, is related to the precipitation and also related to the soil moisture. So if we know these two conditions, then we can try to diagnose whether right now we should irrigate. So it doesn't require much computational time in aiding these irrigation processes.
Okay, thank you. I have a follow-up questions to Marisol. So when you adding irrigations, how do you do that? Like you have some human activity, or yeah, how do you implement the irrigation in the model?
So you can see the slides here, right? Hello?
I see. Yeah, yeah. Okay.
Yeah, so actually we just did a very similar process that the farmers do. So the farmers take the water from the river, and also if the river water is not enough, they take the water from underground, the groundwater. So what we can do in the lenses models, we do the similar thing. Like we can, because the lenses model also including a river model, and also some of the soil layers and the groundwater layers. So you can extract the water and then irrigate it. When I say irrigated, we can think about we put some waters in on top of the soil. So basically, it will make the soil wetter. So this is what we did. And then some of the models use the same approaches, but some of the models use different, because there are a lot of ways of irrigation. Some farmers use drip irrigation. Some farmers use maybe the sprinkler. So there are variety ways of irrigation process. But here in this study, we kind of use a simple way, just try to make the soil wetter.
I see. Okay, thank you. Okay, we have
Sure.
another question. So I think these are big questions. How Indian monsoon is different from Asian monsoon? So you can provide your opinion.
I think in Indian, if we overall talk about the Asian monsoon, actually it's quite big, including the South Asia monsoon, East Asia monsoon, and Northwest Pacific monsoon, and so on. So if we just mention like Asia monsoon is more like even larger scale. But when we talk about Indian monsoon, we probably most of the time talk about India itself. And usually the Indian monsoon itself is starting with around like June 1st. And I'm not sure whether I answered this question or not, but I would like to say Indian monsoon is target on the India, but on the other hand, Asia monsoon is more larger scale. It's like continental scale.
Okay. So next question is, do you think that including irrigation in models can also have significant effect on the estimation of climate sensitivity due, for example, to the effect of clouds? If so, do you think can contribute to reduce or increase current values of climate sensitivity? Yeah, I think it's about the climate sensitivity. Yeah.
Yeah, well, it's hard to answer. So if you, let me hypothetically try to answer this question. So if the irrigation can induce like a homogeneous impacts, for example, like the CO2 is overall global warming, but actually the irrigation, although usually it induces surface cooling, but it also provides more water vapor in the atmosphere. So cooling and moistening, actually, these two effects are kind of competing. So overall, for example, to the boundary layer stability, it's not so intuitive. So it's really hard to say that overall how it might affect even for the cloud processes or the climate sensitivity. Another example is that, as I showed in the last result for the monsoon system, during the summer monsoon, the irrigation actually reduced the summer monsoon intensity because of the cooling over the land and induced the less land sea contrast. But on the other hand, during the winter, actually increases the land sea contrast. So during the summer monsoon become weaker, but over the winter, during the winter monsoon becomes stronger. So it actually has opposite effect on the climate system. So right now, I don't know whether the climate sensitivity will become higher or less, but I think there should be some effects. But it's yeah, it's worth to do this test, I think.
Okay, thank you. Next one is about peatlands. Okay, so peatlands are also one of the land use type, which acts like a sponge and store a significant amount of water and the carbon on the terrestrial ecosystem. Have you looked into the role of these ecosystem types on the sea level change? And do you think they could also play a significant role in determining the flow of water from the land surface?
For me, I didn't look at peatlands. I don't know. I do know that I think in UC Irvine, Anderson's group, that actually they look at how the peatlands, because over the maritime continent, for example, in Borneo regions, there are a lot of peatlands, and then there are also a lot of fire events over there. So I think there should be quite significant impacts both for the carbon and the water storage changes. I think you can take a look of Anderson's group's paper. I think if you are interested, I can provide I can send you about those papers. I think there's some studies about this, but I think they are significant, but I haven't looked at it yet.
Okay. One related question is the soil characteristic properly represented in your model? I think soil type.
And yeah, so usually this soil type is based on IGBP's data sets, and it's kind of global surveyed data that can implemented into the lenses models. But this raises another critical issue, that the soil texture can change, and then how deep the soil texture actually has been surveyed before. So this actually, although we have this kind of information, but it's hard to have this information globally, and especially for the deeper soil layers. So this creates another uncertainties for the lenses model simulations, because this soil texture will affect the hydraulic conductivities in the lenses model or in the soil water fluxes. So I would say yes, a lot of models actually consider, lenses models consider this, but those data sets should be updated. Yeah, this is my answer.
Okay, and the one question from Priyanka is, have you looked into the impact of irrigation processes in the North American monsoon region?
North American monsoon region is like a central US region. Yes, we look at the Ocolola aquifer, because that region is also another hotspot for the irrigation regions. And then we didn't link to the North American monsoon, but we look at the low-level jet. So the low-level jet from Mexico, like Gulf of Mexico to the central US, actually become weaker after we implemented the irrigation process in the model. And also, actually, there's another interesting studies, I think, from French group. I forgot the first author's name. So right now, we know a lot of climate models actually has the warm and dry biases for some regions over the land. Central US is one of the hotspots that climate models usually simulate drier and also warmer. So in that study, the French group, they tried to implement the irrigation in the model, and actually this warm and dry bias has been solved partially. So I think again, although in my presentation, I use California as an example, but the central US actually is another hotspot that the irrigation should be implemented in the model, and at least the dry bias can be partially solved. Sorry, I didn't particularly answer the North American monsoon, but this is some related things that I would like to share.
Next question is, in CIMI 6, which model do you think, especially for rainfall and the wind data, best suited for future scenario of Indian summer monsoon in changing climate? And which tool do you use for the spatial plot?
Well, this is another project. I think I haven't looked at CIMI 6 model in detailed way, so probably I won't be able to answer these questions. And then your second question is which tool? So usually we use MATLAB or NCL or Python for this spatial plot. I'm not sure whether you are asking these technical questions or not. but
yeah, yeah, maybe. Yeah, I think it's good. Yeah, it's fine. Next first question from Olga is, in the areas of the world where land water storage is increased, for example, in South America and Africa, is there a positive correlation with floodings? So it looks like those areas are collocated with tropical rainforest regions.
Yeah, okay, good observations here. That yes, another hotspot I didn't talk about is actually in Amazon during the rainwater storage increases. So in the Amazon, in the past 10 years, in average, the rainwater becomes more and more overlayer. Is related to the floodplains overlayer. But I'm not so sure whether it connects to the old tropical rainforest regions, because it seems like only in the Amazon we can see this signal from the GRACE trend map. So, but in Africa, is further south. That's actually in drier regions with inland river basins. So in South America, actually, yes, it's increased over, it's due to the flooding.
Okay, one more questions. What about the role of permafrost thawings on the sea level rise? Do that play any roles? And the northern latitude have significant amount of permafrost, and which is thawing at alarming rate.
Yeah, it is another project for this one. To my knowledge, right now we are not so sure about the permafrost thawing on the sea level rise yet. Most of the signal is from either from the Greenland and Antarctic or the high mountain glaciers. Those signal from the permafrost actually is quite weak so far. So I think they should play some role, but in terms of the magnitude, I cannot answer right now. But it's definitely a hotspot that deserve a lot of research here, because it not only just for the sea level rise, but a lot of for the carbon is another big issue here.
Okay, I got one more. How atmospheric river concept affected irrigation? I guess specifically in California region, I guess. Yeah.
Yeah, if for the California, usually the atmosphere river is during winter, and most of the irrigation in California is during the summer. So if the atmosphere river brings more snow during the winters, that actually the water storage, particularly for the snow water storage, will become more during the winter, so that during the summer they don't need to pump the groundwater that much, because they can rely on those freshwater river flows from the high mountain snow melting. So if this is one why you want to ask how they connect, I think this is one of the connections that it can provide more surface water irrigation for the California, so that the farmers don't need to pump the groundwater heavily, which is good for California.
Okay, I think one related, yeah, you can just quickly answer. And how about for India? Yeah.
India, what? The atmosphere river?
I guess, yeah.
Are there any atmosphere river in India?
I think maybe not, yeah.
Yes, sir. Oh, thank you. So it's related to the monsoon?
Okay. Yeah, I mean,
I'm not so sure about the atmosphere river.
Yeah, so I think final yeah, I think because of time, I mean, the final questions, do you think humans' interventions are responsible for the rising sea levels, climate change impacts, and excellent initiative and amazing talk. Thanks to all. Yep.
Okay, thank you. And I think, of course, we are responsible for the rising sea levels, and then not only just for global warming that leading to ice melting from Antarctic or Greenland or those high mountain glaciers, but also from the groundwater pumping for the irrigation purpose that actually has a quite significant contribution to the sea level rise. So I think, yes, of course, we as a human, we affect this Earth's climate a lot. Yeah, this is something I say.
Okay, so.
Well, there's one last question.
I think there's one or two more, but I think, yeah, I think we can answer it. Yeah. So what is your assumption on future sea level change? Will it remain the same flow or decrease?
So the result I show today is only till like 2016. So actually there's a huge increases in the rate actually has exponential increase. The sea level rise rate has exponential increases if we use more recent data sets. So I think, will the sea level changes remain the same? Probably not. It actually will increase.
Okay, good. I think one very final quick question. So, yeah, so do you have future projection for the irrigation?
How to predict? Yeah, so the irrigation water actually depends on the human require, like the demand. So it depends on probably two things. One is from the natural perspective is how the precipitation changes, how the temperature changes, because this will affect the irrigation water demand. On the other hand, will be the how much food we will need to provide. So this is from the human perspective. So these two factors we will need for the future projections of the irrigation water.
Okay. So thank you all. I think we should stop here because of time. And
Okay.
let's thanks Min-Hui again. And I hope you enjoy the presentation. And before you go, I want to say several things. So first is the recordings of webinars will be available on YES website, and we'll upload the recording soon. And the second is our second webinar is next Wednesday on July 1st. We have Professor Elizabeth Brownis from Colorado State University, and she will talking about viewing climate signals through an AI lens. And if you have already registered for both webinars, you don't need to register again, but if you want to register, we also provide the link on our website. Okay, so thank you very much, and I hope you staying safe during this challenging time, and hope to see you all next Wednesday. Okay, thank you. Okay.
All right, thank you everyone. Bye-bye.
Thank you, Min-Hui. Bye.
Okay.
Bye-bye.